Let's review the structure of the Salamis tablet. First of all, the Greeks and other peoples believed that the circle represents a whole. Two semicircles represent two parts of a whole. So a number has two parts as indicated by the two semicircles. A fraction, lower grid, and a radix point shift, upper grid, which of course we call a base exponent. The endpoints of each semicircle point to the additive and subtractive sides of each part, what we call negative and positive. For base 60, the tablet accommodates 5 digits, pun intended, for the fraction and 2 digits for the radix shift. We have 5 fingers per hand and 2 hands. Do you think that's a coincidence? I don't. Let's review the operations on the Salamis tablet and understand how you can do these with no memorized multiplication or addition tables. So the first operation is promotion. By the way, in this whole display, we're just going to consider each side of the Salamis tablet as positive. So in the space below a heavy line, 2 pebbles represent 1 on the heavy line above it. In the bottom space, 2 pebbles represent 1 on the line above it. So you can see that in each case, the lines, the value of the pebble below it is 1/2. So here, the middle line, 3 pebbles on the middle line equal 1 in the space above it. The heavy line, every heavy line, 5 pebbles represents 1 in the space above it. Okay, so this is how you promote. If you got 5 here, you put a pebble there and get rid of those. If you got 3, you put a pebble there and get rid of those. 2, put a pebble, and 2, put a pebble. Okay, so how would you have pebble on a heavy line, thin line, top space, bottom space? Well, this one we could replace with 2 of these, right? And so then half is 1/2 of the 2 pebbles. This is equal to 2 of these. So to have it, I just take 1 away. This is equal to 3. So let's see what we've got there. So let's put 3. Now if we segregate them, we can certainly take half of that. How do we take half of this? Well, look up here. We've got a pebble on the middle line, and it's replaced by that for halving. So to have this whole thing, I just do that. To have this, let's look over here. You've got 2, 4, 5, right? So you got 2, which you can certainly have. Let's do that operation completely. Let's replace this with 2, 5. Okay? So I can certainly take half of these 2 and half of these 2 easily. But what's half of something on a double line? Well, back up here, it's this. So let's move that here and take half of each of these. So there's half. So you could say that I memorized these patterns, but I could easily regenerate them just by putting in the count, replacing counts, and then halving the pebbles, taking half the pebbles away. Doubling is pretty much the same thing. Here's the original values. So line, line, space, space. So I just double the count. So this is twice that. Same thing here, but interestingly enough here I could put a 0 pair, and then this is 3, and promote. So this is 3 minus 1, or 2. Doubling this, we know that 2 of those is one of these. Doubling this, we know that 2 in this space is 1 above it. And there we are. Again, I can memorize these patterns, and as I do manipulations, I will tend to memorize them, but I can always go back to putting in the values of the pebbles and doubling or halving them. Let's determine how many pebbles it takes to represent the numbers 0 to 59. That is one sexagesimal digit. So we'll use this space here. And of course this is 0, then 1, then 2, then 3, which can also be represented as 5 minus 2, 4, 5, 6, 7, 8, which can be represented as 10 minus 2, 8, 9, 10, 11, 12, 13, which can be represented this way, 13, 14, 15, 16, 17, 18, which is 10 plus 8, 18, 19, 20, 21, 22, 23, which can be represented that way, 23, 24, 25, 26, 27, 28, there's the 20, and here's the 8, 28, but this is 30, so I can represent that way. So now this is 30 minus 2, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, but now this is 30 plus 20 is 50, which can be represented as 60 minus 10. So this is 50 minus 2, or 48, 49, 50, 51, 52, 53, but this is minus 10 plus 5, so I can make it minus 5. So this is 60 minus 7, which is 53, 54, 55, 56, 57, 58, and these cancel, 58, which is 60 minus 2, 58, 59, 60. So it took us just 5 pebbles to represent all the numbers from 0 to 59. If you keep track of the number of pebbles you need for each digit, each number, and total them up, you get 174. Dividing by 60 to find the pebble count on average per number, you get 2.9, or about 3. So if you assume that you're going to carry 3 pebbles per digit, and you want to do all the operations, multiplication, division, addition, and subtraction, then you'd need a number here, and 2 numbers here because you accumulate into an existing number. I'm assuming that the most you're going to use is one digit for exponent rather than the 2 that are available in general. So you need 3 times 4 times 6, or 72 pebbles to carry around with you, and you'll be prepared for most calculations. Let's see what a pouch containing those pebbles would look like. So here we have our pouch, pretty small. It contains all the pebbles you need to do almost any calculation that you would come across. If you don't have stone pebbles, then you can make some out of clay.